Let's continue to talk about tubular reabsorption and secretion. In this session, we'll focus on reabsorption and secretion of some important substances. First, let's see how sodium is reabsorbed. Sodium is reabsorbed by primary active transport through the transcellular route. Sodium first moves from the tubular filtrate into tubular cells down its electrochemical gradient. Then it is pumped into the interstitial space between tubules and capillaries by the sodium-potassium ATPase. And from the interstitial fluid, sodium is transported into the peritubular capillaries. Together with sodium reabsorption, some other substances like water, glucose, hydrogen, chloride, and urea are reabsorbed or secreted through secondary active transport mechanism. When sodium is reabsorbed through the tubular epithelial cells, negative ions such as chloride are transported along with the sodium because of electrical potentials. That is, transport of positively charged sodium ions out of the lumen leaves it negatively charged, compared with the interstitial fluid. So, chloride ions diffuse passively through the pericellular pathway. Chloride ions can also be reabsorbed by secondary active transport, which involves co-transport of chloride with sodium across the luminal membrane. Urea is the end product of protein metabolism. It is produced in the liver. One of the most important functions of the kidney is to clear urea from the body in the urine. So, plasma urea concentration is often used clinically to assess renal function. Urea is freely filtered in the glomerulus and is not actively reabsorbed. However, this does not mean that all the filtered urea is excreted. As water is reabsorbed from the tubules by osmosis, urea concentration in the tubular lumen increases. This raised urea concentration creates a concentration gradient, promoting the reabsorption of urea. Therefore, the greater the water reabsorption, the greater is the urea reabsorption and the lower excretion. Creatinine is another metabolic waste product. It is an even larger molecule than urea and has no way to go through the tubular membrane. Therefore, almost none of the filtered creatinine is reabsorbed, and thus virtually all is excreted in urine. Another important substance we must mention is glucose. Normally, glucose is completely reabsorbed in the proximal tubule by secondary active transport. Glucose in the tubular filtrate enters the tubular cells by binding to sodium-glucose co-transporter 2. And from the tubular cell, glucose is transported into the renal medullary interstitium by another carrier protein, glucose transporter 2. This limited number of sodium-glucose co-transporters determines how many glucose molecules can be reabsorbed. For many useful substances like glucose, renal tubules have a threshold level of reabsorption. This means there is a limit of how much a substance the renal tubules can remove from the filtrate. Renal threshold for glucose is 180 milligram per deciliter. When plasma glucose concentration is less than 180 milliliter per deciliter, all of the filtered glucose can be reabsorbed because the number of glucose carriers is more than enough. However, when the glucose in the filtrate exceeds this threshold level, the carriers are saturated. Some glucose will remain in the filtrate and appears in urine. The reabsorption rate at which the carriers are saturated is known as transport maximum, the TM. The plasma glucose of a healthy person almost never becomes too high to cause glucose excretion in the urine, even after a meal. However, in uncontrolled diabetes mellitus, plasma glucose may rise to high levels, causing the filtered glucose to exceed the transport maximum and results in excretion of glucose in urine. The condition is called glycosuria. Hydrogen is reabsorbed by co-transport with the sodium, mainly in the proximal tubule. And as the sodium and the hydrogen are all positively charged, they move in opposite direction. So the hydrogen is secreted into the tubules when sodium is reabsorbed. The kidney plays an important role in the regulation of extracellular pH by active secretion of hydrogen and hydrogen buffering within the tubular lumen, including buffering with bicarbonate and phosphate or ammonium. We'll discuss acid-base balance in detail in next chapter. Under normal conditions, all filtered bicarbonate is reabsorbed in the form of carbon dioxide in the proximal tubule. Amino acids are important nutrients for body cells. They are also reabsorbed completely in the proximal tubule by the secondary active transport mechanism along with sodium. Now, let's see how water is retained. Reabsorption of water occurs in the proximal and distal tubules and in the collecting duct. In the proximal tubule, water is reabsorbed secondary to sodium reabsorption. When sodium is reabsorbed, the osmotic pressure decreases. Water then moves from the tubular lumen into cells through osmosis. However, the distal tubule and collecting duct are not permeable to water. Only in circumstances when antidiuretic hormone is produced, permeability in distal and collecting duct increases, and water is reabsorbed. Now, let's come back to the case. Mr. Lin's tests indicate that he has developed renal failure. The glomerular filtration, tubular reabsorption, and secretion are all impaired, resulting in electrolyte disturbances and metabolic acidosis. inadequate erythropoietin production leads to his anemia. In advanced renal failure, hemodialysis or peritoneal dialysis can be used to manage fluid and electrolyte imbalances. But only a successful renal transplant can restore all normal functions. In summary, approximately 99% of the glomerular filtrate is selectively reabsorbed in different segments of the renal tubule. Some substances are secreted from the blood into renal tubule. Most of these exchanges take place in the proximal tubules. After going through all these steps, the filtrate eventually becomes urine. That's all for tubular reabsorption and secretion. Next time, we'll discuss the concentration and dilution of urine.